Going live. 3, 2, and 1. All right. Hi, everyone. Welcome again. Some of you have joined us before. I see some new names. It's a delight to see you all back. And of course, Happy New Year. So I should start with that. This is continuation of a speaker series that we have been doing for years now. And some of you might be familiar with the online format that we switched to during the pandemic. We slowed down a little bit, but the astronomy club still kept going. And that's the cool thing about this, that we managed to adapt to this. Now it's reached a point where we are actually talking about moving back in person and still keep it maybe hybrid so that folks from all places can join us. And also we have been very fortunate to have speakers join us from places beyond the Bay Area, such as a speaker today. So we would like to keep that going as well. And so if you have any ideas to improve the program and just for Astronomy Club as well, just let me know, reach out anytime. And the other programs have also resumed normal operations. So you can go to sja.net, or you can find the full schedule of upcoming events on our meetup as well, which is, if you just search for SJ-Astronomy, you should be able to find all the schedule of events there. So with that, coming to today's topic, I really want to thank you for joining us all the way from Boston. I know it's really late for you there, and thank you for taking the time to talk to us. And Dr. Alan Marscher has been doing his research on black holes for quite some time now. When I saw that he has published like 300 articles and is a professor of astronomy at Boston University, I was like, wow, that's like a long track record of amazing research on supermassive black holes and quasars and other types of active galactic nuclei. So today he's here to talk to us about his research that he has done on the supermassive black holes at the center of the galaxy M87. Some of you might have seen it through your telescopes, and as well as our own galaxy, the Milky Way. So without further ado, I will transfer the controls to you, Doctor. Take it away. Thank you.
Thanks very much, Suhana. And in fact, of course, it's not too late because we're all astronomers, and the evening is just starting. So don't worry about it being late for me. I generally don't go to bed so early. So it's my great pleasure to talk with you about black holes at the centers of galaxies. These black holes that exist at the centers of galaxies are true monsters. They have masses of millions or even billions of solar masses. And so they're real heavyweights. And despite the general nature of black holes not letting out any light, as we'll find, they're actually the most luminous phenomena in the universe. So let me tell you about this. On the bottom, you can see that there's a web page that my research group has. And so if you're interested in browsing through that, you're welcome to do that. It's just www.bu.edu/blazars. Blazars are a type of active galactic nucleus, as you'll find out. And I compose songs. A lot of the songs are around romance and things like that, but a large fraction of them are actually on science. And I sing songs to my classes. And if you would like to hear any of those songs, I'll be playing one for you at the end of my talk tonight. And if you'd like to hear more, then feel free to go to soundclick.com/cosmosii, because my stage name is Cosmos II, son of the cosmos. Okay, so black holes, I think most of you know what they are, but let me just go through the basics. It's a region where the mass has been compacted so much that the gravity is so strong that it sets up an event horizon inside of which anything that goes on can't be seen by the outside world. So nothing can escape from the black hole, not even light. Now, there is an exception. Stephen Hawking found that because of the strangeness of things on the smallest scales, quantum theory, that in fact, small black holes can emit a fair number of gamma rays and eventually disintegrate. by making electron-positron pairs near the event horizon, and some of the matter and light escapes. But for the most part, we can say that that nothing will escape a black hole once it falls in. Okay, the radius of the event horizon for a non-rotating black hole is the Schwarzschild radius, which has a quite simple formula. It's twice Newton's gravitational constant times the mass of the black hole divided by the square of the speed of light. If it's rotating, it's a little bit more complicated, but it's still of that order. So a black hole with the mass of the sun has a radius, if it's not rotating, it has a radius of about 6 kilometers. So something like the size of a medium-sized city. But the ones at the centers of galaxies that can have masses more than 1 billion times the sun's mass, they have black holes about the size of our solar system. So they're small on cosmic, on galactic scales, but they're actually quite large on earthly scales. Now, it ends up that nature is filled with ironies, and one of the greatest ironies that nature has for us is that black hole systems are the brightest things in the galaxy. See, I see I have some chats. Let me take a look. Okay, it looks like the chats aren't for me. And the reason why they're so bright is that as stuff falls in, it can still radiate light until it falls inside the event horizon. And it can take quite a long time to fall in the event horizon. And so as things fall in a disk, like in order to conserve angular momentum, it forms a disk. The disk orbits around the black hole, and through turbulent type frictional forces, it gradually slows down and falls into the black hole. So it takes a long time for matter to actually fall in until it gets very close to the black hole. And as it falls toward the black hole, these frictional forces can make it very, very hot. And as you know, hot matter will radiate a lot of light. So the accretion disk can be extraordinarily luminous, much more luminous than the host galaxies, stars that are surrounding the black hole. Also, in a process which is the kind of the crux of my research, trying to figure out, as matter falls in, it also drags magnetic field with it, and the differential rotation, the faster rotation closer to the black hole than farther out, twists around the magnetic field. And this twisted magnetic field acts like twisting wires and propels particles, highly energized particles, out along the poles of the system, forming a jet. So here's a jet going in the upward pole, and there's another jet going in the downward pole. These jets can be extremely powerful in about 5% of the active black hole systems at the centers of galaxies. Both the jet and the accretion disk tend to be extremely luminous. And so we can see these things at very, very great distances from the Earth. And so they're extraordinarily luminous objects, the most luminous things in the universe, outside of another black hole phenomenon called a gamma ray burst, where when a black hole, we think it's when a black hole with mass of a few tens of solar masses forms during the collapse of its core, and that for a very short time it acts like a super mini active galactic nucleus and shoots jets out at very, very high speeds, very, very close to the speed of light. And that for at least a few minutes can be the most luminous thing we can see in the universe. Okay, so in our galaxy, we actually have black holes with masses of around 10 times the sun's mass, give or take. These black holes form as the remnants of very massive stars whose cores collapsed and whose outer parts exploded as what is often known as a peculiar type of supernova, or sometimes is named a hypernova. Oops, sorry, I pressed the wrong button somewhere. Okay, so that may make you think, okay, there are these 10 solar mass black holes orbiting around the center of the galaxy, all throughout the galaxy. How many of them are there? And are we in any danger from these black holes? So you can actually do an estimate of the number of very, very massive stars that have lived and died. They don't last very long on cosmic scales. They last for less than 1 million years after they form. And so how many of those have died and have left behind black holes that are wandering around space? A conservative estimate of this, knowing the rate at which stars form, is that about 100 million such black holes are in our galaxy. So that looks like an astonishingly large number, and it may make us fear for our lives. We can't see them. It's very, very difficult to detect these things because most of them are starving. They don't have any much mass that's falling into them because there's not that much mass that's close enough to fall into the black holes. So they're accreting at a very low rate. And so they don't produce much light as the stuff falls in toward the center because not much stuff falling in. And so they're extremely difficult to detect. Attempts to detect them, you can kind of see when they pass in front of a star, then you may see the star's light change. And so there have been attempts to measure, to find black holes in that way. And they've had very, very limited success, a little bit of success, but very, very limited success. So are we in any danger of running into one of these black holes anytime in the span of human civilization in the future? And the answer, fortunately, is no. And the reason, of course, is that space is nearly empty. If the sun were the size of a basketball, the nearest star would be somewhere around Australia. The nearest star besides the sun would be in Australia. And so even if they were bouncing around the atmosphere for a very, very, very long time, the chances the two would run into each other is very, very small. So there's not a zero chance, but a near zero chance that we'll run into one for the next trillions of years. Certainly for the lifetime of the sun. There is one of these monsters I've been talking about at the centers of galaxies. There is one at the center of our galaxy in Sagittarius A star. It was actually found by my PhD advisor, Bob Brown. He and Bruce Ballack found the Sagittarius A star radio source using radio techniques back in the 1970s. You can't see the galactic center in visible light because of all the dust that's in the way, but you can see it in infrared light. And so astronomers in both Europe and in the US have been studying the motions of stars in the galactic center region. And there's one in particular, this guy with the yellow orbit here, that is orbiting around something that is essentially, not much light is coming from it. So you see it orbiting around this thing, and that thing that's orbiting around is in this position where there's an artificial star there. Okay, so from the orbit, the size of the orbit, the period of the orbit, you can determine what mass this object has that is going around, and that mass is about 4 billion times the mass of the sun. Okay, so the only thing we know that's that compact is a black hole. Currently, there's not much stuff falling into the black hole, which is probably a good thing, because if there were a lot of stuff falling in, it would become a luminous source of X-rays. It might create a lot of havoc in the central regions of our galaxy, and maybe some of that havoc will get out to us. So it's probably good that our galaxy isn't currently very active, although it probably has been more active in the past. It's not the kind of galaxy where it really becomes extraordinarily luminous like a quasar, but it is one that's luminous enough that it may, in this past, have been a Seyfert galaxy, which is another kind of active galaxy. And as you probably know, in 2020, Andrea Getz and Reinhard Genzel shared the Nobel Prize for this discovery. I recommend that we don't feed the black hole because we don't want to see what happens to our galaxy if there's a lot of stuff falling in. Okay, now it ends up, astronomers were surprised about 20 years ago when we found that essentially all massive galaxies, all galaxies that aren't just little dwarfs, have supermassive black holes at their centers. In fact, the mass of the supermassive black hole at the center is proportional to the mass of the spheroidal component of the stars of the galaxy. So in an elliptical galaxy like M87 here, it's entirely spheroidal. And so the mass of the black hole is in fact quite large, 6.5 times the mass, 6.5 billion times the mass of the sun. In our galaxy, the spheroidal component is quite small, being an SC type galaxy. And so its black hole is correspondingly smaller, only 4 million solar masses. One of the remarkable things about M87 that was noticed in 1918 by Heber Curtis is that it has a jet. Here's the jet seen in visible light. This is with the Hubble Space Telescope, so it's a really high resolution image of the jet in visible light. But you can also see it in X-ray light. You can see it in radio light. And so this is one of those jets of very high energy particles and magnetic fields that I talked about. The black hole systems can shoot out along their poles. So here we have a black hole system, a black hole that's about 6.5 billion solar masses. The mass was determined by the motions of stars in the central regions of the galaxy. So that got astronomers thinking that, hey, maybe that event horizon is big enough that we can make an image of the region around the black hole in M87. And also, since the one in Sagittarius A star in our galaxy is so close, even though it has a lot smaller event horizon radius, maybe that is also big enough on the sky so that we can actually make images using the technique of very long baseline interferometry. Okay, this is very long baseline interferometry, and you use an array of radio dishes that are scattered around the Earth, so you get the resolution as if you had a huge microwave telescope that was about the diameter of the Earth in size. Okay, so the idea is that the hot luminous gas that is orbiting around the black hole in the accretion disk can emit enough, strong enough signal in microwaves, meaning about 1 millimeter wavelength, that we can get very high resolution images using this very long baseline interferometry, or VLBI technique. Okay, so that's a group of about 350 astronomers, of which I was one, make computer simulations to predict what should be seen. And what they found from the simulations, following the where all the light is going. Now, black holes are quite impressive objects, as you might expect, gravitationally. The gravity is so strong that light from outside the black hole, light as it passes near the black hole, bends around it. Of course, some light will fall directly into it, but the light that misses it gets bent around it, and it gets bent into a shape that forms what we call a shadow, black hole shadow, that is somewhere a little bit more than 5 times the size of the event horizon. And so what you expect to see if there really is a black hole at the center of M87 and in the center of our galaxy, you should be able to see a luminous ring surrounding a dark spot. So that's what we wanted to find. You can see what you expect to see from different angles with this computer simulation. So here you're seeing almost the disk almost edge on. Now you're seeing the disk face on. So now as you change the angle that you're viewing the disk, you can see that you'll see somewhat different things. So if you make an image, you can actually tell what the inclination angle is of the disk relative to our line of sight. So the 350 astronomers formed a collaboration, and we nicknamed the array of telescopes, we nicknamed it the Event Horizon Telescope, and that was to get the attention of the funding agencies, because of course these things cost millions of dollars in order to set up. So the concept is that you had to organize, meaning borrowing time from a lot of very high precision radio dishes that are used to observe star forming regions, galaxies where there's lots of stars forming and so on. They have lots of other agenda items in astronomy to do. So you have to borrow time from them for a week or two every year to form a giant array of telescopes called the Event Horizon Telescope, or for short, the EHT. And then you observe the centers of galaxies. So every one of these radio dishes is observing the center of a galaxy at the same time. And then as the Earth rotates, then you actually collect the information you need in order to make a good image. The wavelength that we selected was 1.3 millimeters, so it's in the microwave part of the spectrum. You can't, the visible light isn't coherent enough, it doesn't produce a coherent enough signal in order to do this sort of experiment in visible light. An array for invisible light is a lot smaller, maybe measured in hundreds of meters. Okay, at that size of the array, the resolution ends up being sufficient to image the region near the black holes in M87 and the Milky Way galaxy. Okay, besides me at Boston University, my wife, Dr. Svetlana Jorstad, is also one of the participants in the Event Horizon Telescope collaboration. And it took this huge number of people in order to set everything up, do the observations, interpret the data, make simulations that can be compared with the actual images that are made. So this shows for the observations made in 2017, so about 5 years ago, or maybe almost 6 years ago now. These were the places where the radio dishes were placed. This is in Spain, Pico Veleta in Spain. The submillimeter telescope in Arizona, the submillimeter array and the James Clerk Maxwell telescope in Mauna Kea, Hawaii, the large millimeter telescope in Mexico, ALMA and the Apex arrays in Chile, and then this telescope at the South Pole. So all those, now South Pole can't see M87 because it's the northern part of the sky. So M87, the South Pole telescope didn't participate, but for the Sagittarius A star in the center of our galaxy, is actually very handy to have that, because that's, of course, in the southern part of the sky. Okay, so we got the data. The data had to be calibrated very carefully because the atmosphere affects microwaves very strongly. I got some things appearing that I don't want to appear on my screen. And so what we did in order to make sure that we weren't biased in our making of the image, and the image construction actually requires a lot of delicate care, because the data that you get aren't direct data of the image like you would get for a visible light telescope. Instead, you get a Fourier transform. Your data you have is a Fourier transform of what the image really is. And you don't have all the Fourier components that you need mathematically in order to construct a really good image. So you have to do some iterative process in order to tease out the image. And so because it was a delicate process, involved process, we split into 4 groups that worked independently. And we ended up all getting the same images, which was very encouraging. We observed M87 on 4 different dates and got very similar images, although there are some changes from one date to the next, but they're fairly subtle changes. And so all the images saw this asymmetric ring structure with a dark spot in the middle. Okay. Sorry, that thing that appeared on the screen was more problematic than I thought. Okay, so how's that compare with the computer images? Well, you remember the computer images look a lot sharper than that, but that's because our resolution of our Earth-sized array isn't really as fine as you can make on a computer simulation. So what the theorists making the simulations did was they smeared the computer image with the resolution that you have from the Event Horizon Telescope. And so they made this is what they said that the Event Horizon Telescope should see if the actual image looked like the simulated images. So here's one of the actual images that we made in April 11th, 2017. And you see it looks quite similar to the simulations when the simulations are blurred to the same resolution. So it's very close resemblance to theoretical expectation. And not only that, but the size of the ring here, which, as I said, is a little bit more than 5 times the event horizon size, is that you would expect for a black hole of 6.5 billion times the sun's mass. So we got what we expected, which is really remarkable. You rarely do that in astronomy, rarely get what you expect. Took us a lot longer to get the image of Sagittarius A star, and that's because during the observation, Sagittarius A star changed. It's a fairly small system, and it changes rapidly in time. And one of the things you need to do for the technique is to use, as the Earth rotates, use the different orientations of the antennas as seen from the object out there in the cosmos, the different orientations of the antenna to get enough information to make a good image. And if the information is changing because the object is in fact changing, then that can be very troublesome. So it took a long time to make that. I mean, it was just released a few months ago. Actually, not. It was last May now. So I have warnings about that the image isn't unique. It's not as unique as the one for M87, but it's really what we think is close to what the actual image of the object was at that time in April 2017. In the future, we're going to add more antennas, which will allow us to make shorter exposure snapshots that aren't as subject to the time variations of the object. So we can declare a success, and we really can image the regions near the event horizons of some black holes. We're not sure if there are any others that will be easy to do besides M87 and Sagittarius A star. We're looking around to see if there's any. One of the problems is that a lot of the closed systems don't have very bright microwave emission from around the black holes, and so it's not so easy to get enough signal in order to make a good image. So we've confirmed that the monsters of the centers of galaxies really are supermassive black holes. That's what the theorists had said. And also we confirmed that they appear to have event horizons because they have this black hole shadow that depends on the event horizon being there. So black holes are relatively simple. They're so simple that what we see is actually what the theorists predicted. Again, that's not usually very common for us when we study cosmic phenomena. This has also been found for gravitational waves. I'm not going to talk about them, but gravitational waves have been discovered from merging pairs of black holes. And for the gravitational wave signals, they also follow just what you expect from merging black holes. And so this cartoon is kind of prescient. It's black and it looks like a hole, so I'd say it's a black hole. That's kind of the thing that we are following, is it's got this black hole, this shadow at the center, and it's got the bright stuff around it, and so it really looks like a black hole. Okay, so now I want to shift a little bit and talk about the other research that we're doing at Boston University of black hole systems, and this is to study the systems themselves. What we're particularly interested in are these jets of high energy particles that get shot out along the poles along with magnetic fields. And those kinds of jets produce an enormous amount of radiation that I'll be talking about. Okay, so here's an example of a quasar. This is a active galactic nucleus that's so bright that it outshines its galaxy by thousands of times. And so when you look at this image, you really can't see the host galaxy. And in quasars, the host galaxy is only visible with long exposure Hubble Space Telescope images, where you can see a little bit of a halo around the quasar. And the quasar is contained within a size of about the solar system at the center of the galaxy. When you measure the spectrum of a quasar, you find it has emission lines, as opposed to stars, which usually have absorption lines. And the emission lines are highly redshifted. So here at 7,000 angstroms, or 700 nanometers, is the H beta line that belongs way down here, 486 nanometers. So it belongs here, but the thing is moving away from us so fast with the expansion of the universe, because it's so distant from us, that the H beta line of hydrogen is shifted way over to 700 nanometers. Okay, so it's extremely distant, and yet you see it has a similar brightness to all these stars that are around here in the same image. And so it must be extraordinarily luminous. So these things are the most luminous, steady objects in the universe. The only thing more luminous in the universe is our gamma ray bursts that only last for a couple of minutes. These The emission lines are coming from clouds that are in the outer part of the accretion disk, we think. And you notice that the emission lines are fairly broad. And that breadth is because they're coming from lots and lots of clouds, thousands and thousands of clouds that are orbiting around the black hole in lots of different orbits. And so you get the Doppler effect that is both redshifting and blue shifting relative to the motion of the galaxy, redshifting and blue shifting to broaden out the line. We're particularly interested in my group with the subclass of quasars that are called blazars. This comprises about 5 to 10% of all quasars. And in these objects, there's a jet of high energy particles that's pointing almost right at us. Now, this jet of high energy particles is all the ionized gas, the particles, and the magnetic field that we call plasma. That plasma is moving outward at a speed very close to the speed of light. 5 times, 10 times, or very, very close speed, like 98%, 99.5%, even 0.9995% sometimes the speed of light in some of the objects. That makes it extremely relativistic. And so you have to go to Einstein's equations to figure out what kind of phenomena you're going to expect to see. One of the phenomena is that the emission gets beamed in the direction of the jet. So if the jet's pointing almost right at us, it's beaming this radiation in our direction. And that makes it appear to be a lot more luminous than it really would be if we were looking at it from the side. Also, if something is moving close to the speed of light in our direction, you get the illusion that time is going by much faster, which can cause the illusion that it can appear blobs, these bright spots, which we affectionately call blobs in the business. These blobs, or sometimes knots, are moving outward at apparent superluminal speeds, apparent faster than light speeds. It's just an illusion caused by the fact that the material is moving almost right at us at a speed very close to the speed of light. So it's moving almost as fast as the light waves that it's emitting. And that causes the illusion that it's moving a lot faster than it really is. Furthermore, time gets compressed as we observe it. Now, if you're to observe something moving near the speed of light that's moving sideways relative to you, moving perpendicular to your line of sight, then actually time is slowed down. You get time dilation, which is a famous result of relativity. But if it's moving almost right at you, then the fact that it keeps getting closer to you gives you the opposite effect. It gives you a time contraction. And so things appear to occur a lot faster than they otherwise would. So that means that the light from the jet and the blazar will change its brightness and change its polarization a lot faster than it does in its own rest frame. So one of the phenomena, as I said, is apparent superluminal motion. So motion that appears faster than the speed of light. The speed that you get, if you know anything about relativity, then you know that the effect of relativity can be measured by the Lorentz factor, which is related to the speed relative to the speed of light. And if you have a Lorentz factor of 10, then that corresponds to a speed of 99.5% the speed of light. And if the thing is pointed almost right at you with a Lorentz factor of 10, moving at 99.5% the speed of light, it can appear to move across the sky because of the superluminal effect, appear to move across the sky at 10 times the speed of light. Now, what we see when we look at it is we see one of these blobs that's moving relative to a stationary feature that we call the core. So a stationary feature we think is some place where the particles first get energized so that they have high enough energy so they can radiate a lot of light. The radiation in these kinds of jets comes from very high energy electrons that are spiraling in magnetic fields, causing a kind of radiation called synchrotron radiation. And that radiation can be seen from radio through infrared and visible light and ultraviolet light, and in some cases can even go up to X-ray light. And then the high energy electrons that are in the jet can also run into photons from infrared and optical and UV, can knock those photons up to X-ray and gamma ray energy. So these things are bright from radio waves all the way up to gamma rays. Our group follows about 36 of these blazars every month with a very long baseline array, which uses, it operates at somewhat longer wavelength, 7 millimeters instead of 1.3 millimeters of the Event Horizon Telescope. But at 7 millimeters, we actually get much nicer looking images where we can see the jets, and we observe every month with the VLBA. We observe about 36 of these blazar jets, and we watch as the blobs move away from the core of the jet. This is a montage that was made by one of our graduate students who put all of our images together. So you can see here, for example, here's the black hole is somewhere right around where the point of the arrow there, and here you see the jet coming down here, and it gets kind of unstable and makes a lot of emission farther downstream. If we had gamma ray eyes, blazars would stick out. Along the Milky Way has a lot of gamma ray sources. So for example, black hole systems that are in the Milky Way. But you see these things that are blinking on and off. These are all blazars. Blazars have outbursts of gamma rays that last for typically weeks or months. And so this is sped up this over a 3-month time scale. This, oops. There we go. Over about a 3-month time scale. This thing that's moving down here, that's the sun. The sun is also a source of gamma rays. But these things that are blinking on and off, and really it's sped up so that they're blinking on and off on a time scale of weeks. Those are all blazars. Also, if we had microwave eyes and we looked out, except along the Milky Way where you see things in our galaxy, if you look out, you see mostly blazars and microwaves as well. So it's really because our eyes can see only invisible wavelengths that stars are what stick out when you look at the night sky. Stars and the moon is and planets stick out when you look in the night sky. But if we had gamma ray or microwave sensitive eyes, then blazars would stand out. Okay, so you can go back to this cartoon here. And so what we're seeing when we see these jets, we're seeing these high energy particles and magnetic fields that are being shot out along the poles of the system. And we're trying to figure out all the processes that go into doing this. What makes the particles so high energy? How come everything gets focused so well, and so on. And so to do that, we take these 36 objects that we follow, we observe their images in microwave wavelengths about once a month. And we also follow them in gamma rays. We have NASA has the Fermi Gamma Ray Space Telescope up in orbit. And so it observes every region of the sky about once every 3 hours. And it's not bothered by weather or anything like that. So we have, we can make gamma ray likers, brightness versus time of gamma rays, on a continuous basis. In visible light, of course, we have problems that sometimes the object is only a daytime object and we can't see it, but we get fairly good visible light curves. At Boston University, we use the Perkins telescope in Flagstaff, Arizona, that the university owns. In X-rays, you can use satellites like the SWIFT satellite. It doesn't observe quite so frequently, but we can often catch the outbursts in X-rays at the times that we do observe it. And then we have more telescopes that observe more frequently in the microwave part of the spectrum at millimeter wavelengths. So again, this light across the entire spectrum from these jets of the blazars comes from really high energy electrons that are spiraling in magnetic fields. And so what we try to do is to use the brightness changes and the changes of the images that we see at microwave wavelengths to probe the regions of the jet that are as close to the black hole as we can get. And so this kind of complements the observations that we've done with the Event Horizon telescope. So some of the questions I'm trying to answer is, how are the jets accelerated to near the speed of light? We want to test the theory that this is caused by the twisting of magnetic fields, and that's magnetic fields propel the jets. The reason why they go near the speed of light is because that's the natural speed of the magnetic fields. And even though there's some matter particles that are caught up with the magnetic fields and so can't go quite up to the speed of light, the magnetic fields must be extremely strong in order to propel the jets to such high speeds. Where and how do the outbursts of light occur that we see? We think that maybe shock waves have something to do with it, or maybe when magnetic fields of opposite directions come close to each other, you get magnetic reconnections, or maybe turbulence is involved. We have lots of ideas, and we're trying to test those ideas with our observations. Okay, so we get the microwave images from the Very Long Baseline Interferometry with the Natural Radio Astronomy Observatory's Very Long Baseline Array. And so this is a typical, this is a kind of close-up image of what we see. The black hole is somewhere around here. Things aren't bright there. They don't get bright until you're somewhat downstream of the black hole, where the jet has accelerated up to a speed very, very close to the speed of light. And so we have a stationary feature called the core, and then you have these blobs that form, which are probably something like shock waves that form because the jet isn't steady. Instead, the jet is kind of episodic and being ejected. We get from these images also polarization information, which in the case of synchrotron radiation tells you how well ordered the magnetic field is and what the direction of the mean magnetic field is. So the magnetic field, if you can see these short sticks here, the magnetic field is perpendicular to those short sticks. And so you see in this case, the magnetic field is parallel to the jet. And we can make time sequences from the monthly images, and we can follow these blobs as they move downstream and see how fast they move. And that can give us an indication of how fast the jet particles are moving. So if we see something around 10 times the speed of light, like we do in this quasar 3C273, then we can say the Lorentz factor has to be at least 10, which corresponds to a speed of 99.5% the speed of light. Really extraordinary phenomenon here. And so when we try to put together, we can also make movies. And so on the right, you see the VLBA images turned into a movie. And so you see a blob coming out, a blob being born. It's kind of stretched out in the north-south direction because the resolution is better in the east-west direction than the north-south direction. And we try to be honest by making, convolving the image with a point spread function that is the correct resolution in the different directions. Okay, here on the top in the blue are gamma rays, and you see that this object, we almost dropped it for a while. It was doing nothing to gamma rays for a long time, and fortunately we didn't drop it, and it suddenly started to have outbursts in gamma rays. And then later on it had some more outbursts in gamma rays. You see the visible light it wasn't that well sampled because of the times when you couldn't observe it because it was in the daytime. It was up in the daytime. But you can see that during a lot of the gamma ray outbursts, you also had outbursts in visible light. And here's in the microwave part of the spectrum. So let me get this going again. Okay, so now we're in, see what's the time here? 2011. So that's right in here. So in the 2010 period, when we saw all these outbursts, that's when a blob was emerging from the jet. And then you get more blobs that emerge during these times here. So when we look at the blobs, the times that they appeared, we see here's one blob, B1, blob 1, right when the gamma rays were in outburst. Blob 2 occurred in the later part of the gamma ray outburst. Here blobs, nothing happened much in blob 3. So some of the blobs don't produce strong gamma ray outbursts. We're not quite sure why. Here blob 4 appeared right around the same time as this major gamma ray outburst, and then blob 5 appeared at this one. So we can do this for all 3 dozen objects we have, and so we're having a great time keeping us very, very busy trying to sort out the behavior of these blazars and to see if we see a consistent pattern. One of the problems with blazars is that they do a lot of things at random. And so it's very hard to show whether a pattern, to determine whether a pattern is consistent, is persistent, or whether it's just a fluke, whether it's just a coincidence that you have, for example, gamma ray outbursts at the same time as a blob emerged. All right, so that's what our research is. And we had a colleague who made a movie of some of our research. We had some observations back in around 2000 of the radio galaxy 3C120, where we found that the X-rays, which in that object, X-rays are coming from the inner accretion disk, and their X-rays would drop in their brightness shortly before one of these superluminal blobs would appear in the jet. And so he made an animation and put it to the music of Beethoven's Fifth Symphony. So let me play that for you. It's going to show it from different angles. So when the inner part of the accretion disk goes black, that's when the X-rays decrease. Then a blob comes down the jet. And I have my own music to make for you. As I said, I sing to my classes. And so I will sing for you. Get my guitar. Hope it's still in tune. Seems. Sounds close enough. Attracted by strong gravity, the mass is so compact, pulling me inward, prepare for close contact. No strength to resist, spinning out of control, falling toward the abyss, approaching the black hole. Full of twisting magnetism, feeling hot inside, bursting forth with energy, ready for a high-speed ride. Acceleration growing, focusing the beam. The jet starts flowing, and plasma shoots downstream. Going closer, faster, closer, faster, closer, faster. Twisted field, magnetic spring, propulsion. I'm a superluminal blazar, emission beamed into the night. Check out my relativistic jet, it seems faster than the speed of light. I'm beaming as a blazar in your line of sight. Hop in my relativistic jet, let's go faster than the speed of light. Don't mind the illusions, it's just relativity. Pardon the intrusions into the naked singularity. Enjoy the time dilation. Relax and take it slow. Beam the radiation, make the central engine glow. I shine as a quasar with brilliant intensity, powered by the black hole's ultra strong gravity. I get energized with a shockwave, I get turbulent inside. The magnetic propulsion just can't be denied. Drawing closer, faster, closer, faster, closer, faster. I'm a superluminal blazar, emission beamed into the night. Check out my relativistic jet, it seems faster than the speed of light. I'm beaming as a blazar into your line of sight. Hop in my relativistic jet, let's go faster than the speed of light. Let's go faster! Faster! Faster than the speed of light. Thanks very much. And now I'm happy to take any questions you might have.
I have a question.
Go ahead, fire away.
So how come everybody says nothing goes faster than the speed of light? Now you're saying that, what did you say? Did you say that the jets go faster than the speed of light? Or did you say the accretion disk was going faster than the speed of light? Did you say 10 times the speed of light?
It's the jets, and it's an illusion. It's they appear to go fast. So we always, when we say it, we say the apparent speed is faster than the speed of light. And so what's happening is that and I actually have some math to back it up. Here's some math to back it up, if you think the math backs it up. So what's happening is that it's actually moving at only, let's say it has an apparent speed of 10 times the speed of light. It's moving with a speed of 0.995 times the speed of light. So a little bit less than the speed of light. But it gives the illusion of going faster than light if it's coming almost right at us. And that's because it's moving almost as fast as the light that it's emitting moves. And since we measure what the speed is on the sky, we measure by how much of the sky it covers in a certain amount of time. And our time is all messed up because it's moving toward us at close to the speed of light. Then we get the appearance that it moves faster than the speed of light.
So it doesn't really move faster than the speed of light?
No, the image appears to move faster than the speed of light, but the actual, nothing physical goes faster than the speed of light.
Thank you.
Well, I'm just going to start with, that was a really cool song. I thought it was amazing. I think I can safely say you're the first speaker to sing for us, and that's very much appreciated. Thank you for the wonderful talk. And I was gonna open the floor for questions, as you've already done, and I'm also keeping an eye on our YouTube channel to see if there are any questions coming in. I see there are some 5 or 6 people watching it live as it happens here. So feel free to unmute yourselves. Sorry. I kind of muted a bunch of you during the talk to avoid any background noise. So you have to unmute yourself and ask the question, or alternatively, if you prefer I ask the question or I relay the question, then just put it in the chat and I'll be happy to pass it on. Thank you.
I have a question.
Fire away.
If the speed of light can't, if the gravity of the black hole is bigger than the speed of light, then it seems like it would be faster than the speed of light. Does that even make sense?
It does, but the light is not coming from inside the black hole. That's the key. The light is coming from a jet of particles that escaped from falling into the black hole. They're falling toward the black hole, but then the magnetic field dragged them away before they fell in the black hole. So
then why do they always say that that light can't escape the gravity of a black hole? Why do they say that?
It can't escape the gravity of the black hole once it gets inside the event horizon. But outside the event horizon, all sorts of things happen, because stuff is falling in at close to the speed of light and swirling around the black hole in orbits. it gets very, very hot and can glow. The stuff so eventually most of the matter falls into the black hole inside the event horizon and disappears from our view. It will never, light can never come from it. But light comes from stuff that hasn't fallen into the black hole yet. Or in the case of jets, stuff that almost fell in the black hole, but then got shot out by the magnetic fields. So your intuition is correct that in fact nothing can come from the black hole, but the black hole system produces an enormous amount of light, the most luminous stuff and the most luminous phenomenon in the universe.
So it's like right before it's about to go into the black hole, it just spews back out. And that's what
Exactly.
looks like it's going faster than the speed of light. Is that right?
That's exactly right.
Thank you.
There's a question in the chat channel I'm going to relay. What's the difference between blazars and quasars?
A blazar is a kind of quasar. So in the case of a garden variety quasar, either its jet isn't very powerful or else its jet's pointing towards somebody else in the universe, not toward us. In the case of a blazar, it has a powerful jet that's pointing almost right at us. So this is, they comprise maybe about 5% of all quasars.
Cool.
And of course, we pick them out because they're beaming their light in our direction. So when you look at the sky, that's why when you look at the gamma ray sky or the microwave sky, they really pick them out.
So I have a generic question. So the black hole that was imaged, was it like did the image look exactly like what the scientist expected? Or it was like I'm sure there were simulations done and like there was an idea about like what it would look like.
Yeah, that's a good question. There were a lot of simulations made, and a lot of the simulations looked a fair amount different in the sense that the details weren't the same. But if you took a look at all the simulated images, maybe 100 or so simulated images, a lot of them looked very similar to this the actual image, because we had some information already on how inclined we thought the accretion disk is to the line of sight in M87. So we had a good starting point. If we didn't know how inclined the accretion disk was probably is in M87, then it would have had to make a lot more simulations and would have been a lot more difficult to match them up.
I see. That's pretty cool. Marianne has an interesting question. You mentioned working with your wife. I would love to know what your dinner time conversations are like, but really, really, what challenges, if any, do you have as professionals in the same field?
Yeah, well, one of the challenges, the dinner time conversations often are in our own minds because we had a lot of, she worked down the hall from me. And so we have a lot of the same experiences. And so we're often just thinking deep thoughts to ourselves while we're at the dinner table because we talk so much during the day. But they will often be, did you get the email from such and such? Wasn't that interesting? Wasn't that email interesting? Or I don't agree with that email. What should we do about it? Those are the sorts of things that.
Yeah, that's fun. Yeah, it is pretty. I mean, I haven't heard of husband and wife working at the same university before. Maybe it is more common than I think it is, but that's pretty cool.
It's not very common. There's another pair that worked on quasars, the Allers at University of Michigan, Hugh and Margot Aller. There's a pair at Cornell who work on the neutral hydrogen gas, Martha Haynes and Riccardo Giovanelli. So there's some here or there, but not very many. Of course, one of the things is that scientists are a lot of times the only people we get to meet are people who are at our university or at meetings, and so our cross section isn't so high for the rest of the population.
Yeah, that's true. Rob is sending a question. Will the accretion disks always take the two-dimensional shape of a disk, or can they be spherical around a black hole or any high mass object?
It's possible to be spherical, but they tend to go more toward a disk because of the orbital motion it gives them a lot of angular momentum, and so they have to they can only gradually lose their angular momentum through turbulent type frictional forces. And so they fall in very slowly, but they can fall vertically very, very fast. And so that's true for star forming regions as it is for matter falling into a black hole. So yes, it can be spherical, but it tends not to be because of this the angular momentum issue. Has to conserve angular momentum.
Let's see, I'm checking the YouTube chat to see if anybody has posted a question there, but I don't see one. And no other questions in Zoom chat either. But feel free to unmute yourself, like I mentioned earlier, like if that's the way you would like to go to make it more interactive. So I'm not the only person talking. Okay, there's one more question I see. Does the event horizon have a width, or is it near zero? A near zero line, that is.
It's for a non-rotating black hole, the event horizon is a sphere. It's a in a spherical shape. If the black hole is rotating, then it's flattened, but it's not flattened by that much. Flattened by maybe 1/2 along the pole. It's 1/2 the size that it is along the equator. So it's like a spheroid.
Yeah, I mean that you would imagine it like that because things, like the way I visualize it, like things could be coming at it from any direction, like and then the event horizon is where it changes. So that's pretty
but I think I see. I think maybe they mean at the edge. Does it have an infinitely short edge?
Yeah, is it like an edge? Like, is it like, once you cross that point in space, all bets are off and you're done?
That's a really interesting question because actually the event horizon it's relative to somebody who's very, very distant from the black hole. So if you're in a black hole, you're falling into the event horizon. You don't have it's not like a surface or anything like that. You just pass right through it without any big issues, especially a supermassive black hole where there's not very strong tidal forces because the gravity is about the same on one side of you as on the other side. So the event horizon is in a very particular place as seen from essentially infinite distance from the black hole. But if you're falling into the black hole, what you would notice, you look out and you'll see the time in the rest of the universe being sped up very fast. I didn't mention this, but black holes slow down time, so that as seen from the outside, your time slows down, and so from the outside, an observer would see it take you forever to get into the event horizon. You get the symmetric view if you look at the outside world as you're falling in toward the event horizon. You would see time get sped up, and so you see things happening in a very, very late stage of the universe. That stops when you cross the event horizon. You no longer will be getting photons from the rest of the universe. So it's a funny sort of phenomenon. The event horizon is a funny sort of phenomenon that it's not like a surface or anything like that where you would notice anything in your local region, anything strange that happens as you pass through it. It's really relative to observers that are very distant, that where they will never get your light. If you fall in the event horizon, they will never get any light or any other signal from you.
Cool.
That sounds very Stephen Hawkinsian.
Yeah, that's right. Yeah, nature. nature plays around with time like crazy. I mean, time is when you get into these extreme environments, going very close to the speed of light, or very, very compact, massive object, time gets all messed up.
That brings me to my next question. What did you think of movie Interstellar?
Yeah, they used Kip Thorne, who's Nobel Prize winning gravitational expert,
Right.
to figure out what things would be like if you fell into a wormhole. So while I think that some of it is speculation, they got speculation from the world expert in the topic. So it was
within the
impressive.
limits of scientific, within the realm of possibility.
That's right. It's within the realm of possibility. Exactly right. Yeah.
Okay, cool. Let's see. Any other questions? Oh, there's one more question. Is there a black hole at the center of every galaxy?
When you get to the really dwarf galaxies, probably not. But the centers of all the, what we say, massive galaxies that are, say, somewhere from around maybe 20% the Milky Way's number of stars on up, they all have black holes at their centers. Yeah, that really shocked astronomers when they found that out. That and it's really not very well known how the black holes form at the centers of the galaxies. And that's one of the things that the James Webb Space Telescope is supposed to help us to find out, is how fast black holes grew at the centers of galaxies and what the process was that caused them to grow. Did they start off as, say, 1,000 solar mass star that exploded and made a very massive black hole, and then that just kept accreting matter onto itself to grow and grow and grow? Or did it start out to be a million solar mass black hole before it grew? And the mass of the black hole being proportional to the mass of the spheroidal component of the galaxy is very head-scratching as well. It implies that the black hole and the galaxy kind of grew up together. And so it's thought that maybe when you turn on when it becomes a quasar-like object, that shoots out particles and winds and things that then stop the galaxy from growing for a while. And so the black hole grows, and then it stops growing when too much matter falls in and becomes a quasar, and that stops the growth for a while. And then it after that dies down, then it after you eats all the stuff that's around it, then it starts growing again. So those are the sorts of things that people in the black hole business are working on now.
Did you say that it could start with just one sun exploding? Did you say that?
Well, yeah, but in the early stages of star formation, back in the early days of the universe, when there was just hydrogen and helium, astronomers or astrophysicists who study stars think that you could form stars with about 1,000 times the mass of the sun. Whereas now the most you see is maybe a couple hundred times the mass of the sun, and those are extremely rare. But if you form something with 1,000 times the mass of the sun, it would produce a black hole, which is close to 1,000 times the mass of the sun. And that would be a good start to make a supermassive black hole as it grew and grew over cosmic time.
So you're saying that it would have to be a star that's 1,000 times as big as the sun to start a black hole. Is that right?
To start a black hole that's massive enough to fairly easily explain how it could grow to have millions or billions of solar masses now.
To become a galaxy.
To become the black hole we see at the centers of galaxies nowadays.
Right.
Let's see. Any other questions? One last question, maybe? I know it's getting late. Well, it's not late for us, but it's getting late for you. So it's.
I'm interested in watching on my recording of the San Jose versus Boston hockey game tonight.
That should be a fun one. Okay, I think that's a wrap. Well, thank you so much.
Well, thanks very much for the invitation. I always enjoy talking to enlightened groups like amateur astronomers, and it's always